I hope you enjoyed this video with Sia crashing into the young Earth and then having this spillover that formed the moon. And very likely at the very beginning, the moon was only a couple, maybe 20,000 kilometers above the Earth's surface. There is one of these Ice Age films where at the beginning Scratch finds a flying saucer that crashes through the solar system. And there you see something similar, that the young moon is very close to the surface. And you can imagine the tidal forces are immense. Massive tidal waves at the young Earth. Of course, it didn't really matter because nobody lived on Earth. And of course, there were no oceans at the very beginning. The oceans had to be filled by comets. But these massive tidal forces that led them basically for the moon. If you look to the moon, what do you see? You see these dark spots, or not spots, areas, seas of the moon, according to the Romans. This is basically magma fields, massive magma fields, and they're of course more on the Earth's side that it's going towards the Earth. We had this locking of rotation and revolution. That means one revolution around the Earth, one rotation. So then we always see the same side of the moon. Then there's the dark side of the moon, which is not really darker than this side, but for us it's we can't see it directly. So this is the effect of the Earth to the moon. But of course, the moon is also nearby the Earth. Parts of this angular momentum that was in the revolution around its body intrinsic axis has now been taken for the rotation around the revolution around the Earth. So it drifted away. The momentum stays basically a bit the same, but the distance gets longer. In fact, the moon drifts every year a couple of centimeters away from the Earth. So with time, we lose it. These were the effects of the Earth to moon, but of course, Newton, actio equals reactio, so action equals reaction. The moon is also working on the Earth. One cause is tectonics. And of course, if you constantly work on the dough, it gets hot. This is one of the major sources, two major sources besides the radioactivity, that our core has still this molten component with these convective currents, which make the magnetic field, which traps the hydrogen. One of the reasons why we still have water. Thank you, moon. So he's basically the keeper of the water, of the ocean, or the shepherd of the oceans on this planet, and therefore of the source of life. So that was for me when I prepared this course and learned about all these connections. Well, the next time I've seen the moon, I said a lot. In my mind, I said a thank you to him. Okay. And now let's continue from our planet to the planet where everybody almost, we grow up that with almost a certainty that there are little green men living over there, to Mars. Okay. Oh, I should see the screen, hopefully. There's a pointer. So. Oh. Mars, loads of myth. If we look at it with the pure naked eye, we see a bit of a reddish dot. The red color, where does it come from? Rust. Basically iron oxide. It was also bombarded by comets, and very likely the young Mars had oceans. But, so what we see on Mars is occasionally structures that come from erosion. But what we also see is, for example, this massive, massive canyon here that are coming from tectonics. But this structure is, of course, these structures, the first time they have been seen with a telescope. It was an Italian lad that he wrote something down with canali, which means something like valley. And then somebody has translated canali, channels, or canals. And then Uppsala. Basically the Venice of the solar system. There must be life. And you have a misborn. It's like this genius that invented the monster of Loch Ness. Okay. Well, interestingly, Mars year is 687 days. So once around the sun, it stays 24.5 hours. From the length of the year in comparison to ours, we can directly again use Kepler's third law and calculate basically that the orbital radius is 1.5 times the astronomical units. So it's just at the edge of the habitable zone. So if there would have been enough water, there would be, of course, a lot at the poles frozen. But there might be near the equator then also still oceans. By the way, here, this Vals Marineris that you see here, is 3,000 kilometers long, 600 kilometers across. So compared to this here, the Grand Canyon is the small canyon. It's 8 kilometers deep, so twice as deep only as the Grand Canyon. But the Grand Canyon is clearly erosion. The San Andreas Fault in California, that is through tectonics. And this year is also due to tectonics. It's when the young Mars, the crust, you still had this melting core, which then shifted the stuff along. Then you have also this when you have some tidal forces, or when something is young and hot, the heat wants to go up. And of course, the young Mars also had this radioactive stuff that kept on heating the core, like uranium, thorium, potassium-40. Okay. Oops. I quickly need to rearrange the screen. Okay, but if we have the tectonics, what would we expect with tectonics again? Earthquakes, but also volcanoes. And it happens that Mars has the highest mountain that we know in the solar system. And this is Olympus Mountain. Olympus, the mountain of the gods in Greek. And then whatever Mons means, probably mountain. Obviously, that used to be a volcano. And because Mars is smaller, it could grow much, much higher than on Earth. And it has again something to do how high can mountains, how quickly do they form, how high can they form in the volcanoes, or this is like the Alps when two plates crash, they go up. There's of course how fast do these plates crash, how high does tower up, and how is the erosion. For example, in the Alps, many of the summits are now endangered. Why? Because we have the layers that are twisted, and this means now you have a lot of summits hanging there with a layered structure. And now the permafrost melts. And then you have not only that the ice is not holding the stuff together anymore, it even works as a grease, the water. And you will soon have a lot of summits of the Alps coming down. Okay, but here the Olympus Mountain is clearly a volcano. If to give you a bit of a relation, that's the biggest mountain so far that we know in the solar system. Well, the gas giants, ice giants probably don't have mountains. Gravity is too high. On Venus, we have seen, so now we had a survey of the surface by radar. Mercury, we have seen, is not really something there, so this might be really keeping this title. To give you a feeling, here we have a figure with sea level, Mount Everest, with the highest point on Earth, 8,848 meters. But then we go 3 times as high, about 25 kilometers, this Olympus Mountain. From the dimensions, well, here's Olympus Mons and a map of France. Don't know. I mean, let's see whether course stays with France or will be soon some autonomous territory or okay. So to give you a feeling, I didn't know that it's so big until I have seen this relation. Yeah, now Olympus Mons itself is not really speciality. We see that in its nearby surrounding, there are 1, 2, 3, 4 at least other volcanoes, and probably more. Yet Mars still has a bit in its core, is still a bit molten. But there's no convections, convective currents. This means no magnetic field. Yet, we looked at the iron. Iron is always good. If you had once a magnetic field, iron usually keeps a bit of magnetization. The iron on the surface tells us there must have been a magnetic field at some point. But obviously, when the convective current stopped, it went away. And then no magnetic field. Well, bad luck. The hydrogen will escape. Well, it has only 10% of the Earth's mass, which means the atmosphere it can hold. It's much denser. It's much less dense. It's far less dense, sorry. So it's a very thin atmosphere. And it must be very heavy molecules. Otherwise, the stuff is immediately gone. Or indeed, it's 96% again carbon dioxide, bit of argon, so a heavy noble gas. N2, O2, traces of it, carbon monoxide, but nothing light, no water anymore. It has only 150th of the Earth's atmosphere, so very, very thin for low lighter elements. One interesting consequence is that we have now these bigger molecules. They scatter red light a bit more. The scattering always happens when the wavelength comes towards the size of the object. So they scatter now red light a bit more than blue light. As a consequence, if you see the Mars rovers, you can now watch on YouTube videos of Mars rovers going there on entire days. And when you see that the sunset on Mars, it's bluish. So it's the opposite to the Earth because the red light is now scattered away. And what more coming through is the blue light. Oh. So not really an atmosphere, it's far too small simply. Therefore, the escape velocity is too low. You heat it a bit up and then immediately atmosphere is gone. If it would be closer to the sun, there would be no atmosphere at all anymore. It has two moons, Phobos and Deimos, which are relatively small, so 20 to 28 kilometers and 12 to 16 kilometers. We have to keep here in mind, it's nearby the asteroid belt. The asteroid belt, there might have been a collision, the two of them, or some of them migrate occasionally out. But obviously, Mars has trapped some of them. So these are rather cold moons than that the moon has directly developed nearby. Interesting, Mars, of course, the Roman god of war, then its companions, somebody had obviously some kind of sense of humor, called them Phobos, which is Greek for fear. If you're a psychologist, you should, or psychology, nowadays phobia. If you have a fear of something, Deimos, then terror. Oh, not really, but relatively boring. That was it already, almost what I wanted to tell you about Mars. So let's go now to the Jovian planets. So, Jupiter, Saturn. Jupiter, the big one, for us relatively essential. Saturn also big one, for us essential, so the gas giants, and then the ice worlds. So Uranus, Neptune, 7-8 times bigger than the Earth. Jupiter about 10-15 times as big as the Earth. The structure, well, we would assume mostly of Jupiter, the surface. They have slightly an atmosphere, then comes molecular hydrogen. And at some point, the pressure becomes so high, this becomes metallic hydrogen. That's a state of hydrogen we would like to make more on Earth, but it's so difficult because one needs so high pressures, and we don't get it done. In the center, we assume that there is also a bit of a rocky core. Quite similar to with Saturn. Then Uranus, well, yeah, we would assume there's lots of hydrogen, helium with the methane gas on the surface. There comes a mantle made of water, ammonia, methane ices, and maybe also a rocky core. The same bit on Neptune. Of course, the distances. So Jupiter about 6-7 astronomical units away from the sun. Saturn about 10 astronomical units. What means it's about a light hour. So if 1 astronomical unit is 8 minutes, and 10 is 80 minutes, a bit more than an hour. Uranus, 20 astronomical units away. And then you have to consider always twice the distance means only a quarter of the light intensity. 10 times distance, only 1/100th, so 1% of the light intensity. 20 means 1/400. And Neptune is basically 30 astronomical units away. This is 1/900. So these here are clearly ice giants mostly. But nevertheless, Neptune has quite an atmosphere. That's quite interesting. And Neptune is, for any strange reason, a bit warmer than Uranus. Yet, these here are quite massive. They are close enough to the sun to get enough light. So here, the gases are still above the melting point. Well, melting point of helium. Don't know if it even helium can form an ice. What helium can do is become liquid, and this happens at 4 Kelvin. Nitrogen, 77 Kelvin. Methane should be also relatively low, the melting point. So when you have from gas, or is it sublimation point? If it's above sublimation point, where you basically go from liquid to gaseous phase. This is relatively high, also relatively low. This is also, I think, also 77 Kelvin, 196 degrees minus. This helium boiling point, that's better. When the liquid becomes gas, it's for helium 4 Kelvin, 269 degrees Celsius minus. So these here are mostly icy deserts, but they can still have a lot of a dense atmosphere, at least here for Neptune, this is 50 bar, 50 atmospheric pressure, but mostly helium. Oh, and here's these are 111.5. Well, for Jupiter, of course, what is interesting that we get this structure here, this band structure. These nice bands and less the stuff that we have, that you use with rotating stuff. This comes mostly what is called Coriolis force, that near the equator you rotate basically faster than near the pole, and that you have friction towards the surface. Here you have a gaseous atmosphere that just becomes denser and dense. And now if you let this rotate, then you get these kind of band structures built out, and only occasionally at the layers between, or the borders, you get this enough friction that you get a curl building up, a curl of a storm. If you want to see how this works, there's in the Glasgow Science Centre, just in front of their planetarium, they have a sphere, massive, and if you start rotating it, you will also see that suddenly you get this band structure. So it's just a friction effect. Interestingly, for Jupiter, it builds out here what we call the eye of Jupiter, this red spot, which is a storm, and it has about wind speeds exceeding 400 kilometers per hour. Okay, basically a big hurricane. That's nice, but we have this on Earth, but on Earth they come and go. Right, this year, the first observation was 1820, the first really confirmed. But possibly there were even earlier observations. So a storm that is there for the last 200 years at least. 400 kilometers per hour, okay. Yet, that's not so unusual, these wind speeds. Here is an old Hubble, picture of Neptune. And then we see here the spots structure. Obviously, there seems to be also some kind of cloud fields. And there we have the dark vortexes and bright companion clouds. And what do we have there? Storms. So these are this here is a storm, and they come also and go. But they have wind speeds up to 2,000 kilometers per hour. This is now again because there is the friction with the surface a bit missing, and then you can accelerate like hell, and yeah, nothing is really stopping it. But on Neptune, the storms, they come and go. How about moons? Well, many of the planets have moon. Earth has a big one. We have seen Mars, the two companion ones. Venus doesn't have one, and Mercury doesn't have one. There's an asteroid which has trapped the moon. Well, Eris has one of these dwarf planets. Pluto has trapped quite a big moon. But on the other hand, if you know that Pluto is occasionally going in the Kuiper belt, and there are a lot of objects, then we know that the likelihood that it traps one of these objects should be considerable. So Neptune has quite some. Triton, a big one, but the other ones, again, I would say rather trapped Kuiper belt objects or comets that came in. Uranus, couple of them, and obviously Puck, Ariel, Umbel, Titania, Oberon. Somebody like the Midsummer Night's Dream, in order to give them name. Saturn has much more than shown here. The same is true for Jupiter. Much more, but I think Saturn is no more than 30 moons. But the interesting ones are on Jupiter. First, Jupiter has 4 big ones, but they are relatively close to Jupiter. Here, this is Io, Europa, Ganymede, and Callisto. And then we look at the distance, 421,000 kilometers. Earth to Moon was 350,000 kilometers. But that's almost the same distance as our moon is away from Earth, and is exposed to massive tidal forces. And now guess how it is for a poor moon-sized moon, like our moon. Oh. Same distance, but away from this mass monster, this really big fat giant, Jupiter. So the tidal force must be immense. Must be obviously locked for a long time, but nevertheless, there's still tidal forces going on. Europa is just twice the distance Earth to Moon. Ganymede 3 times and Callisto maybe 6 times. So this is relatively nearby. And if you look at the orbital periods, this is basically 2 days once around the same as what the moon take 1 month. Io does it in 2 days. Europa 2 times the radius. This means pi r squared is the circumference, what means 4 times the how to say, the circumference, and it does it only in 4 days. So they are very fast going around. So very close. Okay, then let's take a look at Io. Io, this is now a true color photograph. So from one of the probes that passed by, and there were no many. think the Voyager ones were the first ones. Passed by the way, this is quite interesting. When you do one of these missions, what happens to the probe if it comes towards a planet? Of course, it accelerates. When is its fastest? When it's very close to the planet. And then it slingshot out, what means it slows down again. This means for you, when you make such a probe, the interesting part is basically the very shortest part. What they occasionally try to do is to have it a couple of times orbiting before then the slingshot is happening away again. Then you get more observation time of the object you are really interested in. This is when you basically start accelerating and running past. This is like when you go to the zoo, and between the animals you walk very slow, but then you start running, and when you're fastest is so that you're fastest when you pass the animal, which might be justified if the fence is broken in the lines. Then okay, and here this is now a true color photograph, and what we see is yellow. What do we usually associate with yellow? Which chemical element? Exactly, sulfur. Where do we find sulfur on Earth? Exactly, next to volcanoes. So here we would expect a lot of seismic activities, a lot of volcanoes. And now, because it's only the gravity of the moon, haha, if we have a good explosion or good volcanic eruption on Earth, like Krakatau or Pinatubo in the 80s in the Philippines, the stuff goes easily up to 20 kilometers. Oh, not to forget the one on Iceland. It's trapped basically half of Europe. Oh, I was back then also trapped, but I was relatively lucky. So I was trapped in Belgium, Leuven, needed to come back to the UK. Suddenly the channel was very big again. Okay, so on Earth it might be 10, 20 kilometers, and then the gravity pulls the stuff down again. And of course, we have an atmosphere that keeps it, slows it down and going up. This is here not the case. And it's quite interesting. So if you want to see an eruption of volcano on Io, take a look at here on this side. I think it should be the second video down. There you see a massive fountain coming out. It's about 200 kilometers high. Cool. Delivering us all this sulfur. So if you want to have a business that needs sulfur, get yourself a spacecraft and fly to Io. So we have the volcanism. In fact, each of these black dots here is a volcano. So Io is the most volcanic active body in the solar system, at least the one that we know of. It's also quite interesting with Io and the other moons. If they're on the side of Jupiter that where the sunlight is shining onto, basically they build up an atmosphere of gas, of stuff that evaporates. In the moment they go in the shadow of Jupiter, it becomes so cold, all these gases freeze down. The atmosphere vanishes away. So we have the gradual buildup and retraction of atmosphere. Not nice conditions for life usually, but So here would be out. We would have basically an iron-rich core, this molten silicate interior, and a very thin crust, which is easily then broken. And we get the volcanic activity. But no water, no life. More interesting would be Europa. We can also expect that there is volcanic activity. Maybe not the super eruption, but still volcanic activity. So iron-rich core, the silicate metal, which is perhaps or very likely still at least hot. We have a thin ice crust on the surface, and very likely we have below a surface ocean. It's just a question, is this water or is this methane? Who knows? Ganymede is, we probably have just an icy upper mantle, but here it's still so hot. At least we have underneath the ice, at least a layer, very likely, where the water is molten. So liquid water, volcanic activity. The Callisto is rather rocky, or mixture between ice and rock. So, a bit boring, but Europa. Volcanoes and oceans. And then we remember back to Earth. They are in the middle of the oceans, especially Atlantic Ocean, where basically the two American and European plate drift apart. With all this magma, hot stuff coming out. This has been called often black smokers, or in the Pacific, around the Pacific Ocean. Basically, the edges of the plates have this plenty of volcanoes. This is very deep. It's very cold. There is no sunlight coming down there. Nevertheless, near these black smokers, it's warm. Loads of minerals are available. And these are oceans of life. So if you find your own black smoker, and usually they're so isolated that all these species, even if they might have developed from the same branch, there are no, all of them will carry later on your name. So Europa is the other planet, and maybe Ganymede, in case there is also a layer of water, are the places in the solar system where, if then there, other life. But of course, it will be rather primitive. From our perspective, primitive. So, and certainly no technology. So no worries, more of the worlds, if they come from another solar system, not from ours. Why? Underwater, you don't develop technology because you have a bit of problem with electricity, especially when you conduct a high power experiment. You do it once, but then maybe we don't know, typically people, at least humans, need 80 years to forget. Therefore, 80 years later, the next one might do the same experiment that with the equal outcome, that afterwards high power electricity technology is dumped for a while. So in order to develop life, we probably need water. It needs to start in the water, but at some point it needs land if it wants to become technological. So that is simple facts. Every technology based or civilization needs to be land-based. With this consideration about life in our solar system, I would stop that video. And then we go basically, how do we look for extrasolar planets? What are the methods? Relatively young science, I think middle of the 90s of the last century, so less than 30 years ago, the first exoplanets were found. Then, of course, everybody was looking for it and looking for smaller and smaller ones, especially Earth-sized ones in habitable zones. But then George W. Bush came along and said, oh, I want to bring people to Mars. George W. Bush had a lot of stupid ideas like invading Iraq and sending out the signal, if you don't want to be invaded by or bullied by the superpowers, get yourself nuclear weapons, like North Korea, then you're fine off. So, global warming doesn't exist. Another stupid idea of George W. Bush. I think this guy was a complete disaster. Not to forget torture. Oh, if it works. So I think this was the most, Donald Trump always counts as the most stupid one because he was the most recent of the complete stupid ones. But George W. Bush was, in terms of mankind, a complete disaster. And if you remember how he came to power, that basically they were too stupid to count their votes in Florida. And when then their first lawsuit, and then after 2 weeks, the judge said, you could have counted again, but now it's too late. Oh, that was really a disaster for mankind. So, especially for the people who have bought a house near coastlines with global warming coming. 80% of its time, the Earth was ice-free. So basically, we still live in the ice age, but we are on a good way to change this again. If you live near a coastline, sell your house and buy it somewhere 50 meters high. That would be my recommendation. And one of the contributing factors was George W. Bush. Okay, enough getting too annoyed with this idea. See you for the next video then. Bye.